Chapter 1.10.3 Pod Overhead. Here is a short summary about the article. Pod overhead in Kubernetes accounts for resources used by the pod infrastructure in addition to the container requests. It's considered during the scheduling, C-group creation, and eviction processes, and requires a runtime class defining the overhead field. Okay, that was the short summary. Let's have a deeper look into the contents. Pod overhead. Kubernetes version 1.24 introduces pod overhead, a feature that accounts for system resources consumed by the pod infrastructure beyond the container's requirements. Calculated at admission time, this overhead considers the pod's runtime class and affects scheduling, sizing, and eviction processes for efficient resource management. Configuring pod overhead. Ensure you use a runtime class that specifies the overhead field. Usage example. In order to work with pod overhead in Kubernetes, a runtime class defining the overhead field is required. For instance, a runtime class like KDA-FC, used with virtualization container runtimes such as KDA containers with Firecracker, can manage this. This class takes into account memory and CPU overheads for computations related to resource quotas, node scheduling, and pod C-group sizing. If only limits are set in a pod definition, the kubelet equates requests to those limits. During admission, the runtime class controller updates the pod spec to integrate the overhead as specified, rejecting pods if the field is predefined. To monitor a workload's pod overhead, it's crucial to assess the updated pod overhead values after the runtime class admission controller's modifications. In resource quota assessments, the total includes container requests plus pod overhead. The kube scheduler, for node allocation, considers the combined value of requests and overhead, calculating the needed resources. For instance, a scheduler looks for nodes with 2.25 CPU and 320 MB of memory. Once scheduled, the kubelet on the selected node prepares a new C group for the pod where the containers are deployed. When configuring resources, if a pod has limits, guaranteed or burstable COs, the kubelet caps C group resources like CPU and memory, summing container limits and overhead in the pod spec. For workload verification, calculating container requests showed 2000 meters CPU and 200 MB memory. Observations later reflected requests for 2250 meters CPU and 320 MB memory, highlighting that node-specific requests incorporate pod overhead as well as container requests. This ensures efficient resource handling in the Kubernetes ecosystem using runtime class definitions. Code example. This code snippet defines a runtime class named KDA-FC with a handler of KDA-FC. It specifies a pod fixed overhead of 120 MB for memory and 250 meters for CPU, which is added to resource calculations for pods using this runtime class. The values for memory and CPU can be adjusted to match the actual runtime and resource overhead in the cluster. This code defines a pod named test pod with two containers, BusyBox Center and Nginx Center. Each container has defined resource limits for CPU and memory. The pod specifies a runtime class called KDA-FC, which will take the memory and CPU overheads into account for resource quota calculations and node scheduling. The code retrieves the value of the overhead field from the pod test pod using the JSON path output format of the kubectl command. This field is included in the pod spec after modifications made by the runtime class admission controller. This code snippet defines the resource requests for a pod, with 250 milli CPU and 120 MB of memory specified. These values will be considered by the scheduler when determining which node should run the pod, and will also be used to calculate resource quotas. This code executes a kubectl command to get the resource limits defined for the containers in the test pod. pod. It uses JS OnPath to extract and display the resource limits, CPU and memory, for all containers within the pod in the JSON output format. The code defines two maps, each specifying resource requests for CPU and memory for a container. The first map requests 500 milli CPU and 100 megabytes memory, while the second map requests 1500 milli CPU and 100 megabytes memory. This code snippet uses the --kubectl describe node command to display information about the node that has the test pod running on it. The --grep test pod b2 part filters the output to show the relevant details that are associated with the test pod, with an additional 2 lines before the matched line being displayed. This code snippet shows the resource requests and limits for a pod named test pod in the default namespace. The CPU requests and limits are both set to 2250 meters, 56%, while the memory requests and limits are set to 320 MI, 1%. The pod has been running for 36 minutes. Verify pod C group limits. To check a pod's memory C groups on its node, one can use the --crick_tl command for CRI-compatible runtimes. This advanced example reveals pod overhead behavior, typically unnecessary for users to check directly. First, identify the pod identifier on the relevant node to find the pod's C group path, which includes its POS container. Here, the path is --kubepods, pod 7F4B 509CF94, 4951. 9417D1087C92A5B2 . The pod level C group indicates a memory setting of 320 megabytes. Additionally, --cube state metrics provides --cube _pod _overhead ** metrics to monitor pod overhead utilization and workload stability.